Earthquakes, often referred to as nature's tremors, are among the most captivating yet destructive geological phenomena on Earth. These sudden, intense vibrations of the Earth's surface have fascinated scientists and civilians alike for centuries. While they are common occurrences worldwide, earthquakes have the potential to cause widespread devastation, making it essential to understand their causes and effects. Here in Digital Learning, we will define earthquakes and delve into the primary causes behind these seismic events. An earthquake is a natural geological phenomenon characterized by the rapid and violent shaking of the Earth's crust, resulting in the release of energy. This energy propagates as seismic waves through the Earth, causing the ground to vibrate and, at times, leading to the displacement of the Earth's surface. Earthquakes can vary widely in terms of magnitude, from minor tremors barely detectable by humans, to catastrophic events capable of leveling entire cities. The point within the Earth where an earthquake originates is called the focus, and the point directly above the focus on the Earth's surface is known as the epicenter. Earthquakes occur due to various natural processes and geological factors, and scientists categorize them into three primary types: tectonic, volcanic, and induced seismicity. To begin with, tectonic earthquakes are the most common and powerful earthquakes. These result from the Earth's dynamic plate tectonics, where the Earth's lithosphere, composed of rigid plates, moves and interacts along plate boundaries. There are three main types of tectonic plate boundaries that generate earthquakes. Firstly, divergent boundaries are where plates move apart, creating tensional stress that builds up and causes the Earth's crust to fracture along fault lines. Secondly, convergent boundaries occur when plates collide, creating compressional stress. The immense pressure causes rocks to deform and, eventually, release energy in the form of earthquakes. Transform boundaries involve plates sliding past one another horizontally, generating shear stress that is relieved when rocks along fault lines suddenly break. Volcanic earthquakes are closely linked to volcanic activity. As magma rises through the Earth's crust, it can cause the surrounding rocks to fracture and create earthquakes. These events are typically less destructive than tectonic earthquakes, but are closely associated with volcanic eruptions. Finally, induced seismicity is also related to human activities, such as mining, reservoir-induced seismicity due to the filling of large dams, and hydraulic fracturing, fracking for oil and gas extraction. The injection or withdrawal of fluids into or from the Earth's crust alters the stress along fault lines, thereby triggering seismic events. While the Earth's dynamic plate tectonics play a pivotal role in generating most earthquakes, it is vital to recognize that both natural and human-induced factors can contribute to seismic activity. Through scientific research and technological advancements, we continue to expand our knowledge of earthquakes, aiming to better protect lives and property in regions prone to these destructive events. All right, digital learners, in this segment, we will explore earthquake waves, discussing the primary types of seismic waves and the methods employed to measure and understand earthquakes. Firstly, let's examine the types of seismic waves generated during an earthquake. To begin with, primary waves, or P waves, are the fastest seismic waves. These waves are compressional and can travel through solids, liquids, and gases. P waves cause a back-and-forth motion of particles in the direction of wave propagation, making them the first to be detected during an earthquake. On the other hand, secondary waves, or S waves, follow P waves. These waves are shear waves that travel only through solid materials. S waves cause particles to move in a perpendicular or side-to-side direction to the wave's path, resulting in a more significant ground-shaking effect. Lastly, surface waves, which include Love and Rayleigh waves, travel along the Earth's surface. While they are slower than P and S waves, surface waves are responsible for the most significant damage during earthquakes. Love waves exhibit a horizontal, side-to-side motion, while Rayleigh waves produce both vertical and horizontal motion. Moving on to the measurement of earthquakes, seismology provides the tools and techniques to quantify these seismic events accurately. Initially, seismographs, which are sophisticated instruments, play a pivotal role in earthquake measurement. These devices consist of a heavy mass connected to the ground and a recording drum that moves with the Earth's motion. When an earthquake occurs, the ground shakes, and the mass remains stationary, causing relative motion between the mass and the drum. This motion is then recorded, allowing seismologists to analyze the earthquake's intensity and duration. Seismologists employ a logarithmic scale called the Richter scale, introduced by Charles F. Richter in 1935 to express the magnitude of an earthquake. This scale quantifies the energy released by an earthquake and provides a single numerical value. Each whole number increase on the Richter scale represents a 10-fold increase in the EI amplitude of seismic waves and approximately 31.6 times more energy released. In addition to the Richter scale, the moment magnitude scale, MW, has become the standard for measuring large earthquakes. The MW scale considers various factors, including the fault's length, slip, and the material's properties, providing a more accurate assessment of an earthquake's magnitude, particularly for significant events. Another important measurement in seismology is the Modified Mercalli Intensity Scale, MMI, which gauges the intensity of ground shaking at specific locations. Unlike the Richter and moment magnitude scales, which provide a single value for an earthquake's magnitude, the MMI scale yields a regional assessment of how an earthquake affects various locations. Earthquakes are a global geological phenomenon, transcending borders and impacting regions across the world. Understanding the distribution of earthquakes is vital in assessing seismic risk, disaster preparedness, and the overall impact on human society. In this part of the video, we will explore the world distribution of earthquakes, examining the regions most prone to seismic activity and the factors contributing to this distribution. Certain regions of the world are significantly more susceptible to earthquakes than others. One of the most seismically active areas, the Pacific Ring of Fire, encircles the Pacific Ocean. It includes countries such as Japan, Indonesia, the Philippines, New Zealand, and the west coast of the Americas. This horseshoe-shaped zone experiences numerous earthquakes due to the subduction of tectonic plates beneath one another. Himalayan region. The collision between the Indian plate and the Eurasian plate has given rise to intense seismic activity in the Himalayan region. Countries like Nepal, India, and parts of Pakistan experience frequent earthquakes as these two massive plates continue to converge. San Andreas Fault, United States, California, particularly the area around the San Andreas Fault, is known for its seismic activity. The tectonic boundary between the Pacific Plate and the North American Plate results in regular earthquakes in this region. Mediterranean Asian Seismic Belt. This belt encompasses the Mediterranean region, extending through to the Middle East and parts of Asia. It's marked by a complex interplay of tectonic plate boundaries, including subduction zones, transform faults, and divergent boundaries, making it susceptible to earthquakes. The world's most seismic regions are typically found near tectonic plate boundaries, active volcanoes, mid-ocean ridges, and areas of significant human activity. Earthquakes, the awe-inspiring natural events that have shaped our planet for eons, have left an indelible mark on the world. While they are often associated with destruction, earthquakes also have intriguing and far-reaching effects that extend beyond mere surface shaking. In this episode, we will explore the multifaceted effects of earthquakes, shedding light on the profound ways in which these geological phenomena impact the Earth and its inhabitants. Earthquakes have the power to dramatically alter the physical landscape. One of the most striking effects is the creation of fault scarps and land uplift. For example, the 1906 San Francisco earthquake caused a 7.5-meter vertical displacement along the San Andreas Fault, forever changing the city's topography. In contrast, subduction zone earthquakes can lead to subsidence, causing coastal areas to sink, which is evident in parts of Japan. Tsunamis. Earthquakes occurring beneath the ocean have the potential to generate massive tsunamis. These towering waves can travel across entire ocean basins, affecting distant coastlines. The 2004 Indian Ocean earthquake and tsunami, for instance, resulted in widespread devastation and loss of life in countries bordering the Indian Ocean, highlighting the global reach of earthquake effects. Landslides and avalanches. Seismic shaking can trigger landslides and avalanches in mountainous regions. These events, often following earthquakes, pose significant hazards to communities in hilly or mountainous terrain. Earthquake-induced landslides can bury homes and infrastructure, causing extensive damage and loss of life. Liquefaction. In areas with loose, water-saturated soils, seismic waves can induce a phenomenon called liquefaction. The ground temporarily loses its strength and behaves like a liquid, causing buildings to sink or tilt. Notably, the 1964 Alaska earthquake led to widespread liquefaction in Anchorage, resulting in severe damage to the city's infrastructure. Beyond physical effects, earthquakes have profound social and economic consequences. They can lead to displacement, injury, and loss of life, while also causing significant damage to homes, businesses, and critical infrastructure. Recovery and reconstruction efforts can take years, impacting local economies and communities. Earthquakes can also influence volcanic activity. The movement of magma beneath a volcano can trigger seismic events, alerting scientists to potential eruptions. For example, the 1980 eruption of Mount St. Helens in the United States was preceded by a series of earthquakes, showcasing the interplay between tectonics and volcanic activity. Following a major earthquake, a sequence of smaller earthquakes, known as aftershocks, can continue for days, weeks, or even months. These aftershocks can be unsettling for residents and hinder recovery efforts, as they may cause additional damage and complicate rescue operations. While earthquakes have numerous negative effects, they also drive societies to improve their resilience and preparedness. Seismically active regions invest in building codes, early warning systems, and emergency response protocols, enhancing their ability to withstand and recover from seismic events. In conclusion, earthquakes are dynamic geological phenomena with a wide range of effects, both destructive and transformative. While they can reshape the Earth's surface, trigger tsunamis, and impact communities, they also provide invaluable opportunities for scientific research and social resilience. Earthquakes are a reminder of the ever-evolving and interconnected nature of our planet, urging us to respect and prepare for the immense power of the Earth's tectonic forces. Thank you for watching. Subscribe to Digital Learning for more videos like this one.